Okay, my talk has this title there. I'm going to talk about relative homology criteria for smoothness. This is a result that I did, that work that we did with Kostiantyn Iusenko, that is a colleague of mine, with Victor Preti, who was a postdoc of both of us, as in this moment he is in the United States. Um, I want to also to say that this work was supported by FAPESP and CNPq, that are financial agencies from Brazil. For simplicity, all algebras here are going to be uh, uh, over an algebraically closed field. Some results require less, some results to be perfect. And in the Stoke, the rings are going to be commutative. Not everything requires this, but it simplifies everything because the paper is on the commutative case. Okay, so I immediately state what is our main theorem. Let B a subalgebra of A, both commutatives, such that B is a finite generated K algebra and A is a flat Criterium B algebra, essentially of finite type. Essentially of finite type means that is a localization of finite type algebra. Then A is B smooth if and only if the relative global dimension is finite. And most of the talk are going to be, I will try to define this, the left and the right side. Okay, so let's talk about relative homological algebra. If some people don't know, this was introduced by Hochschild. And an A modulo M is called relative B-projective or AB projective if M is isomorphic to an induced modulo, a modulo that's given, so it's isomorphic, the direct sum of a modulo like that. An exact sequence of A modulo morphisms is called AB exact if for each I the kernel of Fi is a direct summand, a direct B modulo summand of I. This means that there is a retraction as a B modulo. Giving an A modulo, we define the relative projective dimension of M to be the minimal number n such that there is an AB exact sequence where Pi are AB projectives. Those numbers denoted by the projective dimension, relative projective dimension of AM is denoted by that way. Clearly, if such a thing does not exist, the relative projective is zero, as usual, is infinite, as usual. Okay, so the relative projective global dimension is the supremum of the relative projective dimension, as in normal algebra. Examples, just to see this example is if B is K is a field, then the relative global dimension is the global dimension. In a sense, if B is semi-simple, does always have. And Hochschild has shown that the global dimension of the polynomial rings in any unknowns over B, over any algebra B, the relative global dimension over B is n, generalizing what is well known. Okay, our main theorem was the notion of smoothness. We can translate the geometric notion of smoothing of X using the ring of coordinates of X, K of X. We say that a K algebra of finite type A is smooth if the modulo of differentials is finite generated and locally free. The modulo of differential is thus quotient of I divided by I square, where I is the kernel of the multiplication map. B, this is a well-known result. B is smooth if and only if the ring of coordinates is smooth. And a celebrated theorem of Auslander, Serre, Buxbaum says that F is smooth if and only if the global dimension of the polynomial ring is is finite. Thus requires that the field just requires that the field is perfect. If the field is not perfect, there is counterexample. That is not really true. Okay, let A be a B algebra essentially of finite type. A is called B smooth if the kernel of this ideal is a complete intersection, and A is a flat B modulo. Geometric, this means the following. We take it's well known that there is a duality between the ring, the category of maps of the ring of coordinates, between the modules and the ring of coordinates, and the category and a duality in the category of algebras. Then those two things is saying that the fiber of each element in Y is a smooth subvariety, and also the fibers are varying nicely. This is flatness. Okay, I'm not going in more details. Observe that K smooth is the definition of smooth. So we are really, this is really a generalization of the usual notions. A relative version of the Auslander-Bike-Varus series theorem is our theorems that I stated in the beginning. Suppose that I and B are commutative algebras, so that B is finite to generate K algebra, and A is a flat Criterium B algebra, essentially of finite type. Then A is smooth if and only if the global dimension, the relative global dimension is finite. This characterization leads to some further consequence that I think is nice. The first one is that the relative global dimension can be computed as a sup of a global dimension of some rings. The first one, you take A and localize in the prime ideals. You take with the quotient field, and also the second one you take the fiber at the maximal ideals. You can do both of them, and we then have a result that is an extension of a theorem of Auslander. If given A and B, and seeing this satisfying our hypothesis is wrong there, we have that the relative global dimension of those two rings is the global dimension of AB plus the global dimension of CD. This formula has been a little bit generalized by a postdoc of myself we share a postdoc, no, a PhD student with Kostiantyn, and he proved this with some more or mild things, taking characteristic of the field different from two. He proved this result with some more. So this is in the non-commutative case. So in the non-commutative case, some work is starting to be done. We also have a characterization of smoothness in terms of relative homology in the spirit of the works of the group of the following people. The works of the group BA, Buenos Aires Cyclic Homology Group, the work of Avramov and Michelin Vigée-Poirier, that is close, there's more or less the same results are very related. And then the works of Avramov and Egnar, they did something on the relative, but not another notion of relative. So the result, given extension of algebras, the entity Hochschild cohomology is defined this way. This is the relative entity cohomology. Obviously, if B is squared, if B is K, this is the usual Hochschild homology. Then we have the following theorem. Let B finite generate K algebra and A flat B algebra, essentially of finite type. Then the following are equivalent. The extension is smooth, the relative global dimension is finite, and the Hochschild homology, the relative Hochschild homology groups are zero for I sufficient large. With this, we also get a theorem that I think is nice. Let K be a perfect field, B a finite generate K algebra, and A a flat B algebra of essentially type. Then the relative rank conjecture is true for B containing A. I'm not going to define what's the relative rank conjecture, but it's just the rank conjecture taken to the relative case. I will finish giving some examples. It's X and Y are algebraic variety. We have this projection in the Y, be the canonical projection. Then the relative global dimension is the global dimension of X. Another result is if A is smooth Criterium, if the ring, if the modulus of differential is zero, we say that the extension is etali, and I don't know if it's etali or etali. I think it's etali, and in this case, the relative global dimension is zero, so we get this thing here. Another example to finish, if I take B equals K, the polynomial ring, and A does product here with the diagonal matrix with B, put B in this product taking diagonal in the first and the second, then this extension is smooth, but the relative, the modulo, the relative enveloping modulo, enveloping algebra is not a projective as an A modulo. Just to say that we have, this is a nice thing. Okay, I think I don't have more time, so I'm going to stop here. Thank you very much for your attention.